Uh, so I leave it. I don't know. I kill for the moment the audio.
Yeah,
Or
let's. Oh. That's a long time ago.
No, it's not 2:15.
Oh. Okay.
Do you hear us online? Do you hear us?
What?
Do you hear us?
That's all.
Oh.
That's okay.
Yep.
If I don't come.
Yeah, okay.
Send some form, right? Some
Okay.
Yes.
right signature.
Yes, I don't know yet. I don't know what exactly you
The code of Oral, I mean, let's talk afterwards.
In the standard package, there must be this form.
But I think you have to declare.
I need the people who are not present give their right to signature to the chairman. Hold on, who is the chairman?
You have to come.
Who are the candidates for the chairman?
There will only be 3 people present if you don't come. So, between Costas and,
I cannot give anything to Costa.
yeah.
He definitely does not sign on my
It's
name.
only on YouTube.
Do you really want
Don't
to
say anything.
discuss
Everything
on
you
YouTube?
say goes on YouTube right now, so don't say anything.
I can say it to the world.
Okay, shall we start?
Come a bit in front, don't stay so bad. It's supposed to be open.
What else? Do we hold hands?
No.
Do we sing?
Oh, yeah.
So, good afternoon, everyone. Welcome to the Journal Club by Josef Bender on everything you ever wanted to know about microstate geometries and fastballs, and you were afraid to ask. So,
Okay.
This sentence means very important information.
Okay. So I was told to give this journal club. It's again, I'm trying to review a bit things because they're having a paper by Schenker over the summer about cows and microstate geometries, and there's quite a bit of interest. That people interested a bit in what's going on. So I just want to give a bit of background and for people, especially for people who are not familiar with 20 years of black holes in string theory, just to give them a quick introduction to the subject. So you know that in string theory you can count the entropy of black holes. How do we do that? Well, there's a black hole which has charges corresponding to d1 branes, d5 branes, and momentum. And if you put these d1s and d5 branes and momentum on some circle of radius r, you can ask what's the quantization momentum? And when you have a circle of radius ry, the momentum is quantized in units of 1 over ry. So the 2 pi in front, but I'm going to ignore it. If you have, on the other hand, a d1 brane wrapping this ry circle n1 times, and if you look at 1-1 strings, which are strings going from the D1 to the D1, they go around the D1 brane, but because the D1 brane is wrapping only once, it's a single object, they have to go around N1 times before they come back to themselves. So the momentum is quantized in units of 1 over N1 times Ry. If you have D5 branes, again, you have N5 D5 branes, the 5-5 strings, which are again going from the 5 brane to 5 brane, are quantized in units of 1 over N5 Ry. But then there are these very special strings, which are going from the 1 brane to the 5 brane, which are 1-5 strings. And when the number of the 1 branes and the 5 branes are co-prime, the poor blue guys, they have to go around n1 times and 5 times before they come back to themselves. So the quantization of the blue guys is actually 1 over n1 and 5 times r1. And then the entropy counting is just a counting problem, which is very simple. You have np quanta, so the total number momentum is np over ry, and you have to divide np quanta in units, np in units of 1 over n1 and 5, which is the same as dividing np n1 and 5 in integers, as sums of various integers. So it can be like 1 plus 1 plus 1 plus 1 plus 1 n1 and 5 times, or n1 and 2 and 3 over 2 plus n1 and 2 and 3 over 3, the partitions of this number. And the partition of this number, you can find it by the Cardiff formula. It's not very hard to find it. It's actually square root of 2 pi, square root of n1 and 5 np over 6. It's just a counting problem. It's in the textbook. You cannot ask what's the number of partitions a number has. Now, those of you who know a bit of CFT, this is the central charge. This looks very much like the Cardiff formula, 2 pi square root of c times 0. So it's a Cardiff formula in these guys, in these partitions of this CFT. Now this is not the black hole. And to those of you who know black hole in string theory, there's a factor of 6 which I'm missing. Why am I missing a factor of 6? Because these strings are actually,
This formula is valid when all of them go to infinity at the same rate about it?
this formula is valid, I think, this formula is valid in general. It's not in the Cardinal limit.
It's not always an integer. I mean, a number of particles is an integer. This thing is not an integer.
Well, I mean, the number of partitions, so the number of partitions is e to the power this. This is the approximation for large N1, N5, and NP, I think. But it's large, but it's not in the Cardi regime. In the Cardi regime, NP needs to be much, much larger than N1 and 5. I'm not in the Cardi regime. This calculation is valid outside of the Cardi regime. So I don't need to be in the Cardi regime to get this. So this is the larger approximation. Of course, there are log corrections and so on, that people spend their whole life doing log corrections to this and so on. I'm not going to go there.
For the number of partitions of the product of the three things.
Yes.
Okay, so it all depends on the product anyway.
Yes.
Yeah.
So if I do this, again, if I do this calculation, I get the entropy, and I ignore the fact that there are actually 4 degrees of freedom here. There are actually 4 types of 1,5 strings. There are 4 polarizations, so there are 4 bosonic modes, and it's a supersymmetric theory, so they actually have 4 fermionic partners. And if you know your Cardi formula, the central charge when you have bosons is going to be 4. For 4 bosons, you get a 4, and when you have 4 fermions, you get 1/2 for each fermion. So this is 4 plus 2. So that's a 6. So you have a 6 here because you have, again, 4 bosonic species and 4 fermionic species. And the 6 is cancelled, and you get a nice 2 pi square root of N1 and 5 NP, Stromer alpha. And this is the entropy of black holes in string theory. But there's another way to get a black hole entropy in string theory.
This 6 is not related to some
The original 6 is
any
just,
for central charge or something.
no, the original 6 is just Cardi, partition of N1 and 5 NP. It's just to get the 6 in the square root. That's how it comes. It's just a mathematical question. How many partitions N1 and 5 NP has in terms of sums of integers? And you get the 6. Then again, you get the 6 from the 4 bosons and 4 fermions, and you put it back and you get the black hole entropy. There's a similar example, there's a similar black hole in string theory, which is the F1 NS5 P black hole. Again, it's a S dual of so it can be obtained by dualizing. So this is in type 2b D1 D5P. I can S dualize it, and I can do a T duality, and then I get this particular black hole F1 NS5P in type 2a. Now in the type 2a black hole, what's happening is that when you have N5 NS5s and you bring an F1, the F1 inside the NS5 brace breaks up into something called the little string. So again, you have D1s and D5s which have a common, F1s and NS5 will have a common direction, which I'm calling Y. And you have NS5 brace, and one F1 breaks up into N5 little strings. The best way to see this is to go to M theory. So in M theory, this is the M theory direction. Those are your NS5 brace, they become M5 brains. And your F1s become an M2 brain, driving the M theory direction. And again, everybody is along this Y. I'm not drawing this Y direction where everybody is along Y. But you see that this M2 brain, which is again wrapping the M theory direction, F1 strings are M2 brains wrapping the M theory direction, can actually break. This bit of the M2 brain can go here, and this bit can go here. So one M2 brain can break up into N5 strips. And every strip is a momentum carrier. And as a result, when I have N1, N2 brains times N5, NS5 brains, I get N1, N5 strips. I put momentum, again, this all in the Y direction, so these strips can carry momentum. I put in the Py on them, and I count how many ways can I distribute the momentum Py again, N1, N5 strips, get the same result. I have 4 bosonic modes, because again, this is all inside some K3 or some P4, and 4 fermionic partners, and I get again the 2 pi square root of N1 and 5 NP. So this is the counting, this is called the diagram of the Berlin counting. The other one is the Stromer counting. There's also MSW counting, which Roman is an expert on. I'm not going to go there. It's similar. Now, what's interesting is that if you look at the black hole solution, the black hole is just a simple body black hole, which has entropy 2 pi square root of N1, N5, NP. And however much I dualize, if I do a T duality, an S duality, whatever I do dualize, the entropy of these black holes remains constant. As Dalimil was saying, is the number of partitions. Number of partitions is a number. Numbers are numbers. They don't care about duality. They don't care about the value of the string. They don't care about moduli, the torus size, nothing. This is just a cubic number of states in this system. But dualities, on the other hand, the brain interpretation, the microscopics of this black hole. So even if the black hole remains the same, the microscopics is very different. Here you have N1 and 5 carriers, which come from the strips in M theory. Here you have, again, these bifundamental strings between D1s and D5s. It's a very different microscopic realization, but string theory is very smart, and in whatever duality plane you are, string theory will find for you some microscopic realization. Now, all this story, this is all stuff from 2000 and from 1996. Now, all this story is done ignoring back reaction, ignoring brain interactions. I'm behaving as my brains are just nice objects. I'm putting them on top of each other. I'm completely ignoring their interactions. And the black hole solution is valid when G string times the number of brains is much, much bigger than 1. This picture is valid when G string times the number of brains is much, much less than 1. In M theory, it's a bit more complicated, but these two pictures are very different region of parameters. And the question is, the big question is the following. You can get the entropy of the black hole to get the entropy of the dual CFT. 1-to-1 map, nice formula, 2 pi squared to the norm 5 MP, log corrections, hypergeometric functions, matched to hypergeometric functions. It's amazing. Ruben has worked on Stromer on MSW. It's really amazing. You can do it. It really checks all the boxes. But you can ask a more refined question, which is, okay, great. The entropy matches. What about one particular state? Let's take one particular state here where I have, I don't know, 4 and 5 brains and 2 M2 brains, and I'm putting on this guy, 2 momentum modes, and I'm putting on this guy 3 momentum modes, and I'm putting on this guy 5 momentum modes. Just take one particular microstate. Take one microstate in this regime of parameters, to can count, and ask what's happening if I increase my coupling constant by hand. Again, I'm in string theory, I can increase my coupling constant, I make my electron stronger, and let's track one particular microstate from the regime. So just take one microstate, not all of them, from the regime of parameters where the black hole is counted to the regime of parameters where the black hole exists. What's happening there? And what we found, that what we've been finding for all these years, is that many of these microstates, now even if you think, okay, when you increase the coupling constant, gravity is an attractive force, pull things together, the black hole horizon grows, there's a Horowitz-Korchinski transition point, and you go from having these string theory microstates to getting a nice beautiful horizon of the black hole. But what we found is that many of these microstates, they have no intention to look like a black hole. So if you look at the black hole just like this, and then there's an event horizon at some point, they actually look like a geometry where instead of having an event horizon, you have some amplitude topology, or you have something happening at the scale of the horizon. So the microstates, the particular microstates that give you this entropy, they actually don't give you something with a horizon, but they actually give you something which is horizonless. And this is what we found for some particular microstates, again, which we build. And the question is, can we say that, is it true that maybe all the microstates don't have a horizon? Maybe the solution of the horizon is not due to any pure states, just describes the ensemble geometry, just describes the ensemble of the CFT. This is the big question. And there are two options. You can either say, okay, great, I don't know how to track things from weak coupling to strong coupling. I don't know how to go from here to the black hole, but I can just go in supergravity and try to build things which may look like this. So I can, yes? Some topology and some fluxes. I have a horizon. This is a black hole in event horizon, and running like this. And this thing doesn't have a horizon, has some topology and some fluxes instead of a horizon. So it's just some bubbling geometry which has topology and fluxes. So I can just say I can approach my question in two different angles. Angle number one, let's go to supergravity. Let's build classical solutions which look like a black hole. They have the same mass as the black hole, the same charge as the black hole, the same gap as the black hole, the same length as the black hole. They look like a black hole, quark like a black hole, but they don't have a horizon. Let's try to do that. This is a supergravity exercise. You can ask anybody on the planet. You could have asked anybody 20 years ago, what's the biggest, fattest solution of supergravity which accepts, which looks like a black hole from far away but doesn't have a horizon? And there's a classification problem. Ruben has worked on these things in the past. What is the biggest fattest class of solutions with some symmetry and some supersymmetry and so on? You can just ask the question. There are some equations governing them, and you can build a lot of these solutions. You can just go ahead and build them. And then there's another question. Okay, how much of the phase space do they represent? How much entropy do they have? These solutions. And this is one possible route. But there's another route, which is to say, great, I have some brain configuration here. I can actually try to track one particular brain configuration as I increase my coupling constant. And I can actually look at the back reactive solution corresponding to these D brains and I can keep on backreacting my difference until I go to this regime of parameters, and I can actually follow the solution, the pure state from here all the way to here. That's another option. So I have two options on how to answer the question, what's the dual of a microstate? And it's hard to do. The second thing is much harder to do because it's, you know, if I could solve supergravity equations randomly, I mean, you know, in any system with however many variables I want, you know, I could do it. This system, for example, is governed by some Monge-Ampère system of, like, you know, functions of 3 variables satisfying some Monge-Ampère type equation. It's a nonlinear equation. You cannot just say, I have these brains, this is the solution. Poof. It's much more complicated. It's a bit like localized brains, Ruben. So, you know, if when you have, for example, a localized brain inside another brain, like a D3 inside a D7, it's not anymore a harmonic superposition. It's a much more complicated nonlinear equation. So it's a bit of a similar problem. It's very hard to find these particular solutions. This game, just finding the solution in the bulk by hand, it's a more reasonable game. But, you know, you can just go ahead and, you know, use your machinery to find solutions and so on. So I'll explain a bit what has been done on both routes and, you know, where we are at this point. It's just on the second, just to build objects like this, which look like a black hole, and so on. There's a bit of a problem. And the problem is the following. Maybe you noticed it at this level. I have these momentum modes here. And the momentum modes, because it's D1 brains are wrapped D1 N1 times, and those guys are wrapped N5 times, they have a fractionated momentum. They have a momentum which is, you know, 1 over N5 times Ry. In the Carnot formula, if you ask, you know, what do these fractionated momentum modes correspond to, in the dual CFT, they correspond to L. So normally you have N-1s acting on the ground state to give you momentum. So you put momentum acting with N-1s. But you can also, when you have a CFT of fractional charge of central charge N1 and 5, you can actually act with L minus 1 over N1 and 5. Those are fractional momentum modes. Those are very hard to build in the bulk because I have a bulk, you know, I have a specific solution. I have a solution which is, you know, ADS3 times S3 and on a circle of some radius infinity, and I have some fitted bulk solution. And it's very hard to build in a supergravity solution a mode which has fractionated momentum, which has momentum L minus 1 over N5. Those things are very hard to build. If you look at a random object in this theory, if you put, for example, some gas of gravitons, you can put, for example, some gravitons moving around here, around the circle, they are just, you know, so a graviton moving in this background gives you a momentum wave, but the momentum is quantized in units of 1 over Ry. So if you put a graviton gas here, it's actually going to be L minus 1. You can have an angular momentum, you can have some J minus 1, you can have various things, but you never get, it's very hard to get in the bulk modes corresponding to this operating in the CFT. And we have solutions at this point, which look very much like a black hole. So they have the same as they have an ADS3 asymptotic region, and then at some point there's an ADS2 throat, which goes on for a very, very, very long time, and then at some point there's a gap where the background ends. So there's a huge ADS2 region. So these solutions are very nice. You know, they're called superstrata. They depend on 5 variables. They're the biggest, fattest solutions to Einstein equations ever built. So ever since Einstein built the equation, this is the largest family of solutions anybody has ever built. So, okay, beautiful solutions. The problem is everything you build in the bulk by just, you know, supergravity and some perturbations which are smooth is actually going to be quantized in units of 1 over Ry. And therefore you get solutions which correspond to acting with N-1s in the CFT. Now, L minus 1s, again, they are momentum modes which are quantized in units of 1 over Ry. And you can ask in the D1 D5 CFT, how much entropy can I get if I have a CFT of central charge N1 N5, but I'm just, instead of acting with L minus 1 over N1 N5, I'm acting with L minus 1s. How much entropy do I get in the Carnot formula? And it's a more subtle calculation, but it was done by many people. I think Nate's included. And the answer is not square root of N1, N5, NP, like you get from the Carnot formula. So if you want to get this entropy, you have to act with these guys. You see, there are many, many more partitions of this guy. You actually get this guy to the square root and this guy to the power 1/4. So if you only act with L minus 1s in supergravity, you actually get much less entropy than the black hole entropy. you get the factor of, instead of getting square root of NP, you get 4 root of NP. And this is something which people have realized. So the solutions we have, they are nice supergravity solutions, but because they are in supergravity and because we insist that, you know, they actually correspond to this graviton gas. And the graviton gas in the D1E5 system has this entropy. This is the entropy of the D1E5.
Are stupid questions allowed?
Yes, of course. If you don't mind stupid answers, especially.
Can one do something silly like scale up or down Chern-Simons coefficients in the supergravity? Or work on some covering space or something?
So if you work on a covering space, you can do that. So for example, you can say I have a solution in supergravity and I don't insist it to be smooth in 6 dimensions. I allow some zk singularities. If you allow some zk singularities here, and okay, I put my string theory hat, I say, okay, zk singularities are the 6 branes, they are good singularities. String theory makes sense, you know, I don't care about what GR people say, if you don't like them, you know, I'm a string theorist, I love zk singularities, you know, they are the uplifts of the 6 branes, 20D branes make sense, so if I uplift M theory, I get, you know, top knot space with a singularity with a Z20 singularity, that's a good singularity. So if I put my string theory hat and accept these singularities, then we can actually build some solutions, and that's not something which I did with David Turton and Emil Martin, which actually have a fractionation. So they don't have they are not only L minus ones. If I allow the zk singularity inside, I can actually get an L. I forgot what L we have, but it was clear fractionated mode, L minus maybe 1 over K, where K was the rank of the singularity. So you can actually get some fractionated modes in the bulk. You can get some CFT modes in the bulk, but they correspond to, but they have this kind of zk singularity. If you're willing to accept zk singularities, again, you can put some modes which are fractionated, but it's still not enough. I mean, the ones we are able to put are clearly not enough to give you the full entropy. So it looks like to put fractionated modes. One way would be to put the zk singularities, but then the problem is you work with supergravity. So all these solutions that are done in supergravity, you cannot do string theory in these backgrounds. And these backgrounds are just horrible supergravity backgrounds. So if I have a zk singularity, I have many more degrees of freedom living there. Maybe if I give entropy to those, if I use those degrees of freedom as momentum carriers, maybe I get more. But I don't know how to do these calculations. I mean, that's the main problem is that, you know, so clearly it's one of the root you mentioned, it's a root, and, you know, we took it in a paper several years ago, you know, just said, okay, let's allow some orbifold singularities in the bulk, and we got some promising direction. But unfortunately, we couldn't do too much because, you know, it's a singular solution, so it's hard to put boundary conditions. You just put some wave equation, you know, what boundary condition do you put on a singularity? You have to, it's a hard question. But it could be that, you know, maybe the right answer is that, you know, you have to allow these kind of singularities in the bulk and then, you know, work with them. That's possible. Resolving them is a bad idea. So you can put a zk singularity, you can resolve it, you know, the way the way you take multiple D6 branes, you put them far away from each other, get a top knot. You can break the singularity into a bunch of things. That's a bad idea. That will never give you enough entropy. Somehow you get most entropy by having this zk singularity put together and having all the K-squared degrees of freedom being there and somehow activating them. But I don't have a good geometric interpretation of that. Yes.
So do I remember correctly from the Sanano grid that the fractional mode states in the CFT are associated with spectral flow representations?
Not necessarily. So spectral float. So there are many representations in the CFT. Okay, let me draw back. It's something that I want to explain. So in the CFT, you have. If you look at the states, so this is NP or N0. This is angular momentum. This is angular momentum J. This is where the black hole exists. Above in this range. This is where all the black holes are. In the CFT, you can consider the NS ground state, which is at minus Q over 12 in energy. This is some solution which is just, you know, by itself, all alone there. If you allow zk singularities, you have other solutions here, you know, 1/2, 1/3, 1/4, and so on. You know, you have other solutions at fractions of this thing. If you do a spectral flow, you are going to go. So if you do a normal spectral flow out of this single brane solution, which is this is global in S3 times S3. If you do a spectral flow, you get a solution which has a lot of angular momentum, which is called the supertube. This is an element which is actually G equals to N1 and 5. And here you have all the Raman ground states of your system. All the Raman ground states of your system, so those are states of the two charge system, D1, D5, no NP. NP is 0, so guys, these guys have NP 0. So all the Raman ground states of the system, there are many of them. There are e to the power 2 pi square root of 2 N1 N5 minus J. States, so there are lots of states here, but these states are all known. And moreover, from a CFT perspective, in supergravity, we have them. So we actually understand what they are dual to. So in the D1, they have CFT, we have all these Raman ground states, and they are dual to some solutions, which are called supertubes. There are some brane configurations which preserve 8 supersymmetries, and they can have arbitrary shape. They're quantized. Slavarishko worked on their quantization. There's a lot of nice, beautiful work which you can do there. But those are just two charge solutions. So those are solutions of the system. You see, this doesn't have a black hole entropy. This is just N1 and 5. Black holes have N1 and 5 and P. So this is for MP equals to 0. So there's an entropy here in the Raman ground states. If you do spectral flow will give you here. But it doesn't go inside this parabola. It doesn't go inside the black hole parabola. What we need to do to build our solutions, the ones we have these solutions which have a long throat, you need to act. So we have some supergravity solutions which come from acting on these guys with some J minus ones and some with some L minus ones and some J3 minus ones, which actually bring you inside this parabola. And this is how we get our solutions. Our solutions come, but if you do spectral flow by itself, it just takes you from global ADS to this supertube to some other solution, but it doesn't bring you inside the black hole parabola. So, and here, of course, I can also go here and I can do spectral flow to go here and here and here. But spectral flow is something which goes again in this direction. What you want to go inside. You want to go, this is what you want to go inside the black hole entropy parabola. That's and you also have, by the way, so in Oguri Maldacena, you have these long ADS strings. The long ADS strings are actually corresponding to breaking some of the D1s away. So you have D1, D5s, which are again forming this bound state and so on. Those are like, this gives you most of the entropy. If you take some of the D1s away, so you have to, so if you rip these D1s, you rip one of them away, and you move it out at infinity, then you get these long strings. But it's adding long strings to your ADS is a bad idea in terms of entropy. If you're an entropy hog, just want to get as much entropy as possible and you don't care about anything else, the best is to put all your branes together, merge D1s, all the D5s, all the D1s, clump everybody together, put everybody at the same point. That's how you get most entropy. The moment you start moving some of the branes away, taking them on the Coulomb branch, entropy drops down on you. So this is the story again. So this is the story for the from a CFT perspective. Again, these solutions they come from acting with some combination of L minus ones and J minus ones on the CFT, and they're nice solutions, but they are graviton gas solutions. They are not solutions which have this fractionated structure. They don't have a 1 over N1 They don't have a 1 over. They are not obtained by adding 1 over N1 characters. On the other hand, they have a mass gap. So because these solutions have a very long throat, you see here, there's a very long throat. You can say, okay, great, I have a long throat. Let's put the mass gap above supersymmetry. So supersymmetric solution, and let's not put this decay singularity. Let's just build a supersymmetric solution, and let's put some waves. I can put some waves, leaving at the bottom here, some harmonics, and I can ask what's the mass gap between supersymmetric states and supersymmetry breaking states. Now, in the D1D5 CFT, we know what the mass gap is. The mass gap is supposed to be exactly this quantity. So if I put right moving momenta and left moving momenta, for example, the first, the momenta are quantities in these units. So the gap between the ground state, the supersymmetric ground state, and the first excited state is actually 1 over N1 and 5 Ry. This is the case for the D1D5 CFT. And you can do the same calculation in the bulk. You can take the solutions, again, asymptotic ADS and S3, with a huge long ADS throat, and then some garbage at the bottom. And you can solve the wave equation. There are some of these solutions which are called 1, 0, and superstrata, and there are some other solutions where you can just solve the wave equation. And what you find is that there's a mass gap, which is actually, this is supposed to be really 2. That's an exact number, because you have momentum on the right, momentum on the left, and they meet each other, and that's where the gap corresponds to really having left moving momentum. So if you draw the spectrum of the states from a CFD perspective, I have at energy equals to 0. This is my total energy. I have all the supersymmetric states. Again, they're equal to S states living here. Then there's a gap, which is exactly this 2 pi over another 5 Ry. And then you start having more and more states, and you can build the states by putting excitations on top of this. But there's a gap which is really 2 over another 5, which comes from the bulk. You can see it in the bulk from these capped geometries. You don't need to do you just have to solve the wave equation in this string backgrounds. So this is how the spectrum of the CFT looks, and it matches this. I mean, so if you just compute again excitations on top of the geometries, you get this kind of picture. That's so again with the gap from the supersymmetric state to the first one, which is exactly given by the CFT result. So this is the story. So you see these geometries, even if they're obtained with graviton gas, again they're obtained with L-1s. They have this feature that even if I'm building them with L-1s, if I compute their mass gap, the mass gap behaves as if I had acted with some L-1 over N5s, which is a strange thing. Now, if you ask me what's happening, this calculation of the CFT dual is done at the Fiorbeck point. So this D25 CFT is not known in the corner of the modular space. It's free only at some point. It's like n equals 4 diagonals. It's free when G string times n is much smaller than 1. And these solutions are valid at the opposite corner when G string times n is much bigger than 1. And when you go from the orbifold point to the supergravity point, it's possible that this dressing of these operators can be you can actually get some extra contributions to these operators, and it's possible that maybe these L-1s break up and you actually get some other. So again, this description in terms of L-1 is valid at the Fiorbeck point, but when you move away from there, it's possible that you actually get some of these fractionated modes on top. It's very unclear. But what is clear, if you just go to the supergravity point, you do the wave equation, you solve, you find these modes, and you find this gap, which is exactly the one you want in the CFT. So this is a good, and then you can also compute, for example, the 2-point function in this thing. So the 2-point function in geometry corresponds to a heavy operator in the CFT. And you can see that the 2-point function in geometry, for example, has the right, has some dip, which is the black hole result, and then for a long time it looks like a black hole, and at some point we see some garbage coming up. So this is the kind of behavior you expect in a typical state in the systems. There's a dip, and then it's hard to see the ramp because it's a single geometry. To get a ramp, you need to get all the geometries, but that's a more complicated game. So anyway, this is the story for the solutions you build straight in supergravity. So if you just go in supergravity, close your eyes, that's what you get. Maybe there are questions before I move to this.
How does it compare to the mass gap of Luca and friends?
That's exactly the same.
Same.
Yeah, it's the same.
The 2 and do they not?
I think they get the 2. They must get the 2 because it's the CFT gap. So the CFT, so Luca says, we get the CFT gap. And the CFT gap is 2 over n over 5 Ry. And ours is also the 2. I mean, and then for a long time we thought it's over the 1 and something, but Pierre did the calculation for this D25 things, and it really came as 2 over n over 5 times Ry. So it is exactly at the same point. Now, what's happening for these geometries and what I was hoping to find in Luca's result, but I couldn't, is the following. If you look at one geometry, let's put all my geometries here. If I look at one geometry, and this is 1 over 2 over n1n5, 4 over n1n5, 6 over n1n5. If you have one geometry, I perturb around it and I get one solution here, one solution here, one solution here. So the spectrum above one particular ground state, I get this tower of states. Now, those numbers are not exactly 2. In some larger limit, it's a 2, but the distance between this guy and this guy can be like 1.8. And the distance between here, so the distance between the first and all the others, it's more or less the same. It's 1.8. These can be 2, but the other guys are varying. On top of a different state, here I build another tower. This is also around 2, but those guys are let's say a tiny bit at a different distance. On top of another tower, I build another thing. This guy is also around 2, but then the other guys, maybe they're more spaced out, like that. So if I'm to draw all of them, so I ask what are all the states of the theory. I put here, I have e to the power s states. So I have all the supersymmetric states, one here, one here, one here. The supersymmetric states have a gap, these guys have a gap, these guys have a gap. If I look at the full theory, so all the possible bloody states, what I should see the gap. Then I see a lot of states around here, but then I want to see a tiny bit of dip. I want to be in the total density of states, I want to see some sort of dip. When I go between 2 over 5 and 4 over 5, I want to see a pattern like this, with maybe some stuff here, maybe some stuff here, and this thing becoming wider and wider. Of course, the further out you go, the difference between these gaps are, becomes larger, and you don't see anymore any of this tower structure, but you actually see. So you see something like you have some states here, and then you want some sort of oscillatory structure, which then wipes out into something constant. That's the kind of behavior I was hoping, and I talked to Luca and I talked to all these guys doing it, and I couldn't find it in their thing. But then Chiming Chang was here 2 weeks ago. He had this fortuitous states in N=4 Mills, and he's computing their entropy, and he's computing them also in N=4 Mills. And he had a graph in his talk at strings where he was computing the mass gap in his fortuitous states. And it looked exactly like the one I wanted, with a bump, and then another bump, and then the bumps wiping out. So there I could see the bumps. Now, maybe the bumps go away at large n. Maybe his bumps are just weak coupling, and with strong coupling they go away. Maybe a strong coupling you only have look as a result. I don't know. But when I saw those bumps, I was like, wow, bumps. I've been trying to get bumps out of those guys for ages. And Luca and Gustavo, they kept telling me, no, there are no bumps. We just see a nice. So they're just seeing a nice clean spectrum like this. They don't see any features in the spectrum, any type of bumps on the spectrum. But again, they are doing some JT gravity, they're not doing full string theory. So maybe in that particular theory there are no bumps, but the ones, in N=4 super Mills, which has a nice clean string theory dual, there are some bumps in Chiming Chang's talk at strings. So maybe there are bumps. I really hope there are bumps. But that's my expectation of how the spectrum of this theory will be. And that's basically so this is more or less the physics of these guys. There's another way. So these solutions are horrible. Again, they depend on 5 variables. They're again the most complicated solutions we can think about. But there's a very simple way to understand them intuitively. There's a very good intuition which we are figuring out right now. We are finishing a paper with Nick and Emil Martinez. If you look at the original, maybe I should draw somewhere else. Let me erase here. If I have an original ADS3 times x, I have an ADS3, which I'm drawing like this. That's some sort of hyperboloid. When I put momentum on this solution, what's happening is that this ADS3, so this is actually global ADS3, but I did the spectral flow. So I have a global ADS3 solution, and I did the spectral flow, which is again in this case is mixing up angular momentum with some of the momentum. So I got from energy minus C/12 to energy 0. So I have a Ramon state, a Ramon ground state. So the Ramon ground state is not dual. It's not. It's just a coordinate transformation of global ADS. But if I glue it back to flat space, the Ramon ground state has an angular momentum, which is N1 and 5. The Ramon ground state is really a spinning object. This spinning object is known as a super. The spinning objects are known as super. They are the duals of the V1 ground state. Now, when I add momentum to the super tube, again, I have a momentum wave, I have a horrible calculation, we do this very complicated thing to build the superstrata. What's happening is that this momentum takes a region of this global ADS and really gives you like an elevator. Makes up this region of, this is ADS3 here, there's an ADS2 region, and then at the bottom, you still have the same global ADS as the one you have here. It just functions as an elevator, just makes your solution deeper and deeper, which is what you want. And there's a momentum mode running around here, around some location around this thing. And all these solutions, which have again a long throat and they have the right mass gap, and they're the beautiful ones and so on, all of them they look like this. They look like global ADS on which I'm adding some momentum mode at some location. The black hole in contrast is an infinite. So the black hole is just an infinite solution, it goes on forever. So these solutions, there's an approximate way of thinking about them. Instead of like building the full solution of 5 variables and spending 1 year to understand the solution and to work them out, there's a quick and dirty way to do them, which is just to take a super tube and to add some momentum wave in some location, and you get exactly the same physics as our fully backtracking solution. The price is that again, this momentum wave is not going to be smooth. You have to put some singular momentum wave. When you put a momentum wave, you have to put some singularity, but you actually get the right physics. You get the right mass gap, you get the right location of the momentum wave, you get everything on the nose by just approximating this geometry with this momentum wave with a singular momentum source there. So it's a quick and dirty way. I mean, if you want to get an introduction to the geometry to understand how they are and what their physics is, this is the cheapest way to understand them. You just have a momentum wave running around here. It's the momentum which keeps the ADS2 throat open. Why do you have an ADS2 throat? The ADS2 metric is like r squared dt squared minus dt squared plus dy squared plus dr squared over r squared. This is ADS3 metric. If you have empty ADS3, when you go to r equals to 0, this y direction shrinks. So that's what's happening here. The y direction, this is the y direction here, it shrinks. And so it becomes 0 at this point. But when you put momentum on the y direction, when you put momentum on y, you get an extra factor in front of here, which has some sort of 1 over r squared, plus some more stuff. And because you have momentum, so there's an NP here, the momentum on the y prevents it from shrinking. The momentum mode keeps it finite because again, when you have a momentum on a mode, if you shrink it too much, you get a centrifugal force. The thing will split up. So this is why this ADS2 region appears, because this guy is preventing the y direction from shrinking. So the y direction stays constant, and you just have an r squared dt squared and a d squared over r squared. That's an ADS2 for you. So you get an ADS2 because you have this momentum, and at some point here, this is where the momentum sits. The moment you go below this momentum, the momentum wave sits here. The moment you go here, the y direction says, hey, I have no more momentum. So, let's shrink back. So the y direction stays constant here because of the momentum holding it. But the moment you go below this wave, the y direction just comes and, poof, shrinks, and you get a smooth cap. So that's somehow the way these solutions are. And the black hole solution, the textbook black hole solution, has this momentum source, again, inside the horizon. So, it's really an infinite ADS2 throat for the black hole. These guys are a finite ADS2 throat. So that's the physics of why the solutions exist and how that's why you get this ADS2. That's why you get this ADS2 throats. So at this point you have 3 possibilities again for the black hole, because again I told you I didn't know about this U115. I told you that we don't have a CFT understanding of this mode. There are 3 possibilities for the physics of the black hole microstates. Again, the question is, I count the entropy using black hole microstates. I take the black hole microstate to the regime of parameters where the black hole exists. How do the microstates look like? Option number 1, there all be geometries. So one possibility is that all the microstates of the black holes are going to be geometries. Smooth. Now, when I say all, I don't say all. I don't mean all. I have a Hilbert space. In the Hilbert space, there are some coherent states. The coherent states are dual to geometries. They have a semi-classical limit. The quantum superposition of geometry 1 and geometry 2 is also a state of the CFT, but doesn't have a geometric description. So when I say all the microstates, what I mean is that the coherent states are span the Hilbert space. So my Hilbert space of states is spanned by geometries which are nice and smooth. Option number 1. Option number 2, if I look at this Hilbert space, there will be geometries which are there and smooth, but the typical states, which count the black hole entropy, they will be given by some string theory singular stringy configurations. This is option number 2. So the typical states will be given by some stringy configurations, which I cannot calculate. I cannot do anything with them because I don't know how to do string theory in one-on-one backgrounds. And there will be some weird guys, which are the smooth guys, very special guys, which I'm working on, like this L-1. So for example, maybe this L-1 over 5 will all be singular and stringy. That's a possibility.
This is like multi-gravitons things.
Those are multi-gravitons things. So those are multi-graviton states. They are basically, I mean, I can act with these guys. I can act with many of these graviton gas operators. So multi-gravitons are all going to be giving me smooth solutions. But the multi-gravitons are L-1s. They're not L-1 over 5. And as Ruben was saying, maybe if I put an orientifold, an orbifold singularity, then I get L minus 1 over N1 5, but then it will be stringy and messy, it will not be given by supergravity. And option number 3, not be a horizon. Typical state will not get a horizon. That's also something which we are not excluding. We cannot exclude naively. But what we know, we have a lot of evidence that it will not be 3. And there are several places where the evidence comes from. Point number 1, again, if you want to get the mass gap correctly in the bulk, the way to do it, you have the typical states which give you these long throats and something at the horizon. So these points that, at least you get the typical mass gap from those. So those will give you the good mass gap. Also, if you look at the typical states, they have no isometry. The molecules in the room have no isometries. So every molecule configuration in the room breaks the transition invariance, but the gas, if you just describe the gas as an ideal fluid, it doesn't break the transition invariance. So the horizon has an invariance, has an isometry, while the random state should not have an isometry. And in the bulk, you cannot build anything without isometry, it doesn't have a horizon. So random states could be either like this or like this, but no isometries. Isometries should not exist. The pure states of a system should not have any isometry. The moment you have isometry means that you are actually looking at something, you're averaging over something, you're ignoring degrees of freedom, you are smearing over something, you are not. The moment you get isometries, you cannot get pure states. Pure states should not have isometries. Molecules in the room, they don't have any isometry. Random configuration molecules, there's no isometry in the molecules. But the gas in the room, the average description, of course, there's an isometry. I can move around, I don't feel any force. So the gas has an isometry. The ideal gas description of the room as a fluid has isometries, but the typical states don't have isometry.
Is the theorem?
Do you know any system where the typical states don't have isometries? I don't know any system. Any system on the planet where which has a lot of entropy, all the states break the isometries. The moment you put isometries, you restrict. That's the rough picture. And then this is one indication that the mass gap is captured by those. In the D1D5 system, again, if you look at the D1D5 CFT, in the D1D5 system, you have to get here. The D1D5 states are actually singular. If you look at the typical D1D5 states, they have a strong curvature. They are not described by supergravity. They can be described in some sigma model as a string configuration. They can be described, but as some, but there's no supergravity description. Supergravity breaks down. So the typical states in the D1D5, they are more in category 2. And at the end, I want one argument because again, I've been talking with Dalimil at some point and Derek about the two charge about the CFT1. So you can take, you can ask also in the, you can take all the geometries. Again, they have a nice ADS2 throat and they have a cap. And you can take a limit where they actually become ADS2 forever. And then these solutions would be some solutions which have an ADS2 UV and an infrared cap. And there's another solution which is an ADS2 UV and some other infrared cap. And you can ask, what does it mean for the CFT1 dual to this ADS2? There's a CFT1 dual to this ADS2, and this CFT1 seems to be a very nice CFT. Now, why is it a nice CFT? Point number 1, I can put excitations. So this CFT1 has degrees of freedom. Point number 2, I have various operators which get webs. So it's a CFT which has many operators of many dimensions. If you just look at the solution which is infinite ADS2, so the one corresponding to a black hole, so this is just ADS2 going on forever. And you can assume, so there's a question, what is this dual to? Those guys, they are dual to some operators. So these guys are dual to some heavy state, to some heavy operators of the, to some heavy state of the CFT, which are also supersymmetric. So this is heavy state 1 is dual to this guy, heavy state 2 is dual to this guy, and they're all supersymmetric. They all have zero energy. I'm calling them heavy because the heavy is my D1D5 language. They're not really heavy. They have zero energy. They're all supersymmetric ground states. So then there's a question: is this dual to any state? Does there exist a state in the CFT which is dual to this, infinite ADS? And this would be, let's call it heavy 0. And in particular, the state heavy 0 would preserve conformal invariance. Because again, infinite ADS2 preserve conformal invariance. Those guys break conformal invariance in the infrared. In the UV, they have conformal invariance. You go to the infrared, they break conformal invariance. Pociski-Strasser, Kleber-Strasser, Rubin knows, normal holography. GVPZ, all the good old examples. The point is, if this guy exists, if the CFT has a heavy state, has a ground state which preserves conformal invariance, you can actually prove, and it's a simple argument, that the energy momentum tensor of the CFT1 has to be zero as an operator. Now, if this is zero as an operator, it means two things. First of all the correlation functions in the CFT are just step functions. There's no dimension. There's no size. I mean, the only thing which when you compute the two-point function in the CFT, the only thing that you get is if the operators are like this or like this. It's a step function. You cannot get a function of T1 minus T2. So this theory, as a result, is topological. Sorry. There's an operator which you can realize that, so there's a conformal superconformal transform, there's a dilation, there's an energy, and there's a superconformal transformation, and you can realize them as a stress energy tensor in this as an integral of if the dual CFT is local.
I mean, that's right. If the dual CFT is local, if a CFT generally is local, there's a stress energy tensor, but it has to be traceless. So in one dimension, it's just a traceless one-nonlinear matrix, so it's zero. So it's the volume. There are all these examples of normal CFTs, actually, in fact, in boundary conditions. Yeah.
But this CFT, on the other hand, that it's local because I can compute two-point functions. I can look at this state of the CFT, so I can look at because again, this guy is not alone. This H0 is not alone. I have many other ground states. I have H0, I have also H1, I have also H2. If I look at the solution H1, I can compute the two-point function. I can compute, correlations. So this CFT, because it's dual to supergravity solution, which is nice and beautiful, it's a local CFT. I can do, my locality in the bulk, for example, in this particular geometries. So the CFT is local, and
except it's not really a CFT because it's a DQFT.
it's a conformal quantum mechanics. But
are you talking about the theory which has the conformal invariant ground state or the other?
No. So the point is, no, I'm in ADS CFT. The moment I'm in ADS CFT, I have a theory living in my ADS dual to my ADS UVs. That theory, I know it's a theory. I don't know what it is. Now that theory I know by construction because I just built this object that it has some ground states which break conformal invariant. Let's call them heavy 1, heavy 2. I build a lot of them, e to the n1, n5, and p to the 1/4. So I build a lot of those guys. Then the question is, does the CFT also have a ground state which preserves conformal invariance? Does the blue guy exist or not? And the point is, if the blue guy exists, you can show that the CFT is topological. But the CFT is not topological just because I can build these guys which are very happy. If you only had the ADS2 theory, if you didn't have any of those, so if you played in some toy model of ADS2, for example, and you don't have any of these microstates, then you say, great, I have a CFT which has one conformal invariant ground state, H0, it's a topological theory, everything is hunky-dory. But because in string theory, when you build these ADS2s, you always have these extra geometries, which all are supersymmetric. They are ground states, but they break conformal invariance. Therefore, the theory is not topological. So then from a CFT1 perspective, the argument is that a pure state can be dual to this, or to anything else, as long as it's not conformal invariant. This guy shouldn't be dual to anybody. So there's no state in the CFT which is doing option 3. It's either option 1 or option 2. Either they are supergravity solutions, or they are some singular stringy solutions, which I don't know, maybe they are both. But they are not going to have a horizon. A horizon comes, again, has isometries. It comes because I'm averaging over them. I'm ignoring degrees of freedom. That's why a horizon comes. So if you guys remember the Shrek movie, and I'll conclude here, there's like this fairy godmother, and, they discuss with the ogre. So she says, oh, we lived happily ever after, but, no ogres. And she goes and says, Thumbelina, no ogres. Snow White, no ogres. Hansel and Gretel, no ogres. Beauty and the Beast, no ogres. And she says, no ogres, no ogres, no ogres, there are no ogres. And, it's the same here. D1D5 system, no horizons. No horizons, no isometry. D1P, no horizons. CFT1, no horizons. You don't get the horizon. The pure states of these guys are not going to have an event horizon. The pure states of this CFT. The pure states break the isometries. They break conformal invariance. They give you this nice, beautiful guys. But there's no state in the CFT dual to this. This is illegal in the CFT. This has to be thrown away. That's basically the conclusion from this game. So that's why this is more or less the gist of the effort. Now, of course, there are questions, so for example, Steve Schenker was asking, if you just take, for example, random geometries, which are D1D5 geometries, if you take those guys, if you compute, for example, chaos, you get chaotic behavior. There's a supersymmetric chaos for D1D5 black holes. That's a question. You can compute chaotic behavior in the CFT. It's a weakly coupled CFT. Maybe it's chaotic, maybe it's not. Maybe the chaos becomes stronger at strong coupling. There are many questions which you can ask. But at least, given what we can build and given these two arguments, there seems to be that the horizon is just an artifact of smearing, averaging, ignoring degrees of freedom. If you take a look at all the degrees of freedom, you never get the horizon. That's more or less the gist of this. Yeah. So, questions? Shoot. You're supposed to be screaming. What about Euclidean? What's bad about the horizon? Euclidean black holes are great.
Bringing up this monotonous versus fortuitous story again?
Yes.
You probably have more to say about that.
Yes.
Yeah.
Yeah. So the point is, so these guys, which have n-1, they are exactly graviton gas. And graviton gas, as you showed you, gives you these solutions, which are supposed to be, so which again gives you these particular solutions here, and they correspond to monotonous states, meaning there are states where when I have a graviton gas, I have a graviton here. If I make my d1s and d5s different, then the states are still going to be there. I put more brains, I make a bigger radius. If I have the mode which has 35 oscillations on the circle, that's a good graviton gas mode, and that's still going to be there if my radius becomes smaller or shorter. In the D1D5, this doesn't happen. You see, if I have a mode which has a 1 over n1 mass gap, if I bring another n1, if I bring another n1 here, either like that, but if I don't want to bring like that, I want to look at the typical system of the system. If I bring another n1 in this system, so again, I make my n1 go like this and then come like that and like this. So I just bring another n1 in the game, and then I screw up completely my mass gap situation. So let's suppose I have 1 over 19 times 20. This is the number of d1s. And this is the number of the 5. So my mass gap is 1 over 19 times 20. So I have all the guys which have L minus whatever number this is. If I bring in another D1, then I screw up this thing completely, because if I bring I take away another D5, I get equal numbers of D1s and D5s. So then if I go around 19 times, I'll come back to myself. So all my modes which gave me entropy, all these guys which have L minus 1 over 19 times 20, when the number of my D1s becomes 20, all these fractionated modes, they actually stop existing. So I only have modes which have L minus 1 over 19. I don't get this huge fractionation. I get a much lower fractionation. And this is the same phenomenon as the fortuity. Fortuitous states, when I change my rank, so I have some matrices which have some relationship between them, which give you these fortuitous relations. The moment I change my rank from 17 by 17 to 18 by 18, what was a fortuitous state for n equals to 17 is not there anymore for n equals to 18. They only exist at some specific, so you fix the rank, and then you find fortuitous states. But you cannot change the rank and get fortuitous state. The fortuitous states disappear. So you only have them at some values. Same happens here. In the D1D5, again, take again 19 D1s and 20 D5s. Then the mass gap is over.
Isn't it easier to think just about in terms of 1 over n1, n2? And yes, when they are equal, you just have special properties for squares.
Yes, but also if they're both even, for example, the mass gap drops down. So if they're both even, so let's say I make this okay, for 19 and 20, I have the mass gap, which is the.
That's okay, because there is a square inside. If they're both even, then there is a square of 2.
Yes, but I lose entropy. The states, because the point is, if I have, so let's say I have 1 over, so if I counted 1 over n1, n5, and they're both co-prime, I have to divide np in units on 1 over n1 and 5. If they're both even, then I have to divide NP in the number of times I can go around without coming back to myself. So it's really NP in terms of 1 over N1 and 5 over 2 or 4, I forgot. But I lose, but you know, if I do that, I get my entropy, it's not going to be 2 pi square root of N1 and 5 NP. It will be it will have a factor of 2. So I have a drop in entropy, and you know, the number of states goes exponentially down when the two numbers are even, for example, or if the multiples of 3. And you know, if they're equal, then my entropy drops like crazy. So this phenomenon that, you know, when you play with numbers and, you know, for a fixed value, everything is hunky-dory, you change the number a bit and your states just, you know, poof, vanish. This is the same as the fortuity phenomenon. This is the phenomenon in the D95. Now, in the bulk, the solutions we have, again, they have, except the ones with orientifolds, with orbifolds, which, again, we don't have a good CFT understanding, they actually have L-1s. L-1s are not fortuitous. L-1s are just graviton gas. You put a graviton gas, if I make my N1 bigger or smaller, I don't care. My L1s and L-1s are just going to be the same. So in a sense, the solutions have L-1s. They are like the how they call it, the non-fortuitous, or what? Monotonous. They are monotonous states. So you know they exist at any value of n. The guys with L-1 over N1 are fortuitous. That's the difference. But the distinction between them and saying that because the states are fortuitous, they must be dual to a black hole by itself. This is the bait and switch. Because the point is, if I give you a state, you know, let's suppose I compute some state in the CFT, some heavy state. If you want the state to be dual to the black hole, so let's suppose I have a state and I propose that the state is dual to the guy which has a horizon, to this guy. If I have a state dual to a black hole, if I compute the expectation value in this heavy state of some operator, which breaks the SO4 invariance of the black hole, this guy should be 0, sharp 0. In the black hole background, the black hole is spherically symmetric by all the GR theorems on the planet, proven for, like, you know, everybody and their brother. Black holes are unique. In the black hole solution, I should not get a web on the boundary CFT, which is dual to an operator which breaks my isometry. And if we compute this operator, so again, you know, microstate geometries, you can compute these operators. You can compute, for example, the web of some L equals 2 mode in this background in this microstate geometry. You get a number. It's a small number, but you get a number. You get something. You don't get 0. You only get 0 if you have a spherically symmetric solution. So for the fortuitous states, one can do a calculation, which I told these guys to do, Chiming, and you know, they're probably doing it right now. Take a fortuitous state, take another fortuitous state, and take an operator which breaks the conformal invariance. Some L equals to 2 modes, you know, some very simple thing which breaks the which breaks the isometry of the black hole horizon. If this guy is 0 on the nose, straight, for all the possible operators like that, then okay, arigato gozaimashita, you know, black hole, no problem. But if this number is not 0 and it's equal to something, then, you know, it's hard to see that this is a black hole. So the fact that fortuitous states don't have this. So again, our solution at this point, they have this L minus, I mean, you know, they have this L minus 1, they are dual to L minus 1s. But it doesn't mean that if I have a fortuitous state, it will have 0 webs for all these operators, and therefore it will have a horizon. This is where the bait and switch happens. You know, just because, you know, monotonous states are dual to geometries, but fortuitous states, you know, just because a state is fortuitous doesn't mean that it's not dual to geometry. And I have another way. So this is one way to go to this. There's another direction in which I can show that, you know, so I can build fortuitous states not in the D95 system, but I can also build them in the F1 and S5P system. And there I can control the entropy, so I can get all the fortuitous states, and I can show that they're not going to have a horizon. They'll get webs of some operators. But that's something which, you know, I can discuss it on a side. But that's the relation. So in principle, you know, if I had fortuitous states, again, compute with guys and see. Maybe it goes like 1 over n. Maybe it's exponential. Maybe it's equal to minus n. And you know, maybe when you go to large n in supergravity, you don't see it anymore. It looks to be 0, and ADCFT is stupid and cannot see it for them. It's also possible. So because you expect the black hole results to get some corrections, but the corrections are going to be small. So maybe it's correct. Maybe it goes down in the black hole limit. I don't know. But this is the calculation. If you want to show that something is dual to a black hole, you have to show me that all the operators, all the webs of all the operators in a heavy state, are going to be 0. And that's a very hard thing to do. That's the.
Can you say a little bit more about the spectrum of this putative conformal quantum mechanics / CFT1? Like what is known about CFT data of that theory?
Oh. The only thing which is known is that there's a huge amount of heavy states. So this solution, I have a supergravity solution, asymptotically ADS2, Poincare ADS2, so it's supersymmetric. It has basically zero energy. It has the same and it breaks conformal invariance in the infrared. So that's some state. I call it H1. I built another solution which has,
I guess, do you expect the states to organize into multiplets of the conformal algebra, even though there is no conformal vacuum?
How would the conformal algebra act on them? So there's a dilation operator, but I don't know how to dilate in the bulk. So if you allow me to put here some region where ADS2 goes into something else, some near ADS, like the way people do for this JT gravity, people put this near ADS here, and then then I have a notion of distance. I have a notion of distance from here to here. I can make these guys more shallow or more deep. And I have this notion of dilation, of my geometry being dilated, and but for that I need to have this near ADS region or some flat space region. If I have ADS2 forever, so if I'm a guy, I would have this geometry back in 97. And Maldacena I had this thing, and I have all these solutions asymptotically ADS2. I don't know anything about ADS3, I don't know anything about ADS4, I just know ADS2. You want ADS2? Here's a solution, ADS2 asymptotics, and some throws. But when you have ADS2 asymptotics, this L doesn't make any sense, because again, it's an infinite ADS2, so I don't have any notion of scale. It's just one. The only notion of scale is here. It's at the bottom. I have some solution which has some topology, and it's there. There's no notion of dilation from that perspective. So I don't know how to see the multiplets.
Another question. So at the beginning, you said if you take one microsecond safety, and then people can show that if you turn up the coupling, you see some topology. Is that showed in some explicit?
You see some
example?
You see horizon, or you see what?
Then you see some topology like bubbling geometries without horizon.
Oh no! So that's the whole point. So if I take a geometry, if I take a D1 and I look at the typical guy like this, I don't know how to build this in supergravity, and I cannot track it. I cannot track again this D1 D5 with this guy here. I cannot track these solutions all the way to supergravity. I don't know what's happening. The only thing I can do, I can build things directly in supergravity, and I can ask what is it dual to. And most of the guys are dual to L-1s. Some guys which have orbifold singularities, they are dual to fractionated modes. But I just build them in supergravity first. I impose smoothness, no horizon, 3 charges, supersymmetry, and supergravity just gives me what it gives me. I'm just a blind guy. And then I can do CFT. Then I can compute heavy light, or heavy light, and I can match. So for example, there are many papers which compute heavy light, this kind of operators, and they compute them at the orbifold point, and they compute them in the supergravity point. This is a protected operator because this guy has 4 supersymmetries, and if the operator is supersymmetric, there's a protection. This one is protected, and you can actually mesh heavy light from the orbifold point to the supergravity point, and there's a one-to-one map. And it's a very beautiful match which has been done by Giusto and Rodolfo Russo and all these guys. They are basically, there's a whole machinery of people who do precision ADS holography and who compute these guys both in the bulk and in the boundary. So we have a good identification of our states. We believe we have a good identification of our states at the orbifold point. That's but some other quantities are not protected. For example, the mass gap is not protected. If you look at this heavy, say if you look at the mass gap of these things, in the CFT at the free orbifold point, the mass gap is over the 1. But when you go to the bulk, again, the solution gets a very long throat, and the mass gap is over the 1/5. So this 1/5 calculation is actually not done at the orbifold point. It's done fully in supergravity, in the backcorrected regime. That's the only place where you see this very low mass gap, and you see some kind of chaos behaviors, and you see all these problems. In the CFT is very stupid. It's a free CFT, so it doesn't see this very low mass gap.
Is it possible that the order of limits, like matter, that the fact that you are starting on supergravity and does this matter?
For this ADS2 limit, when I take this ADS2 infinite road, in principle, I can just play stupid and say, great. Forget about ADS3. It's very confusing to think about ADS2 if you have ADS3 in the back of your mind, because your ADS3 intuition is very different from the ADS2 intuition. The most stupid thing is to say, look, I don't know anything about ADS3. I'm in the M2, M2, M2 system where there's no ADS3. I just build a solution which is flat space going into ADS2. Most of the black holes in string theory, they never have an ADS3. So you just have a black hole which is flat space ADS2. You go there, throw away all the ones in the harmonic functions, you get an ADS2 solution. That's your solution. That's much better to think. If you think about this limit, you know, in the D1E5 PCFT, how do I go to the ADS2 limit? It's a very confusing thing. It confuses people for ages. The best way is to just work and to just say, I'm a supergravity guy. I have want the CFT dual to CFT1 dual to ADS2 in string theory. What are all the solutions asymptotically ADS2 Poincare, which I can build in string theory? Question. I just build those guys without any limit. If you think about limits, you get confused. Just build all the solutions homework with ADS2 asymptotics and anything in the bulk you can put, which makes sense in string theory. And you'll get those guys. You'll get these guys.
Can I ask that because in this work of Pedro Vieira and it seems he was looking, they were looking at if from the point of view of n equals 2 if you keep finite n and you go to is strong coupling, yes, you you only get Helmut gravitons. But if you do a first large n and then you
larger string, then you get
yes, then you get some small string that is very heavy. That should be, I think, this two.
Yeah, normally the way I think about it is, you know, I take some large finite number of branes. So I take like an n to be 10,000, and then I play with G string. That's the cheapest way to think about it. So, you know, like I'll go here. So I have like, you know, 10,000, so 19,000 D1s, and I have 20,000 D2s, D5s. So when G string is, you know, 1/1,000,000, this is good. It's a good description. G string sometimes is much more than 1. I keep my n fixed because my entropy is my n. My entropy is really a number. It's really n1 and 5 np to the 1/2. So that's frozen. I want to keep frozen entropy. I don't want to play with n and so on. And then I just increase by hand my G string. I make my G string bigger and bigger and bigger. So when this number is over the 1/10, I still have a good string theory. String theory is very happy with G string over the 1/10. But this guy has a big supergravity back reaction, and it gives me these solutions. It gives me this long throat solutions. That's the way to think. I mean, the best is to freeze n. Freeze n to be large and frozen, and then move G string back and forth. That's the best way. That's the way I prefer to work. MSW, no MSW.
More questions? Let's thank Joseph.
Before we go, as I was mentioning in the email, we would like to take this or use this opportunity to discuss the speakers for the next semester.
Maybe we can stop the Zoom and
yeah,
stop the whole.
but maybe I don't know.
People in the Zoom may want to.
I stopped YouTube recording.
Can you stop my YouTube?
Can I stop? No.
No, I need to log in.
No, actually. I cannot takes it. Just one Zoom per computer.
Yeah, so that I can log in and then I can make myself out. I can make myself in a plain code.
Okay. So yeah, in fact, for the spring seminar, we already have 2 speakers. So one of them is Gunnar Behan, who was suggested by the owner, right? And he's probably going to speak about CFD's bootstrap, right?
You get several options, yeah. Either both a couple of minimum models or it's gonna be for the CFD.
Okay. Then we have Rishi Umar from Cambridge. I'm going to talk about
Monopoles and standard.
monopoles. Yeah, and then I would say at least 3 more names. So should we invite and maybe then some backups?
So it'll take us to March.
So we will start with Connor, who I mean, that's like 20th of January, and then we're supposed to go until the end of May, or
But for now, we should just schedule winter months.
Okay.
Okay, it's too early.
let's see how many names we can put together, right? So there are some.
Let's go to my office and stop it from there, because it's not here. Let's stop the YouTube. This is public, so you know, you guys see that, no, don't invite them.
So should I wait? Or?
Maybe not, but just be kind.
Oh, so far I didn't say anything. Like...
Say who we want in both.
Okay. So I just wanted to put on some suggestions, right? So okay, that I can do, right? So Ruben was suggesting
But there's the YouTube, so I guess, yeah, principals. YouTube watching on there.
You're still broadcasting this on YouTube.
Really?
Yes.
Why? I don't know.